All right, so not in this lecture video, we're going to talk about the products you can make when you use nitrogen as the nucleophile in these nucleophilic addition reactions. So let's start off with aldehydes and ketones reacting with a primary amine. So one quick note on terminology here. When we talk about primary, secondary, and tertiary amines, we're talking about how many carbons are attached to the nitrogen here. So in a primary amine, you have one carbon attached to the nitrogen. Secondary amines, two carbons attached to the nitrogen, and in tertiary amines, you have three carbons attached to the nitrogen. So if I take a primary amine and I react it with an aldehyde or a ketone, what you're going to do is you end up replacing the CO double bond with the CN double bond to make an imine. We're going to see that the reaction is, and what I want you to, before I go into the mechanism here, I want you to keep in mind that the mechanism is very similar. But one of the things to keep in mind is that nitrogen, the difference, there's a major difference between nitrogen and oxygen, is that oxygen likes to make two bonds, whereas nitrogen can make three bonds. So if you kind of think about it, oxygen, when it adds to something, it can make two bonds, right? So if I have if I do an so I guess what I'm trying to say is that when I have a nucleophilic addition with oxygen, that oxygen is only going to be bound to two things. If one of those things that it's bound to is already a carbon, then you're not going to have that oxygen be bound to make a double bond. But nitrogen, it has this ability to add twice, okay? And we'll see that in the next slide. So the way this works is these reactions, again, are carried out under acidic conditions. So what happens here is the nitrogen is actually is nucleophilic enough to attack the carbonyl carbon of the ketone or aldehyde. You make this intermediate here. Now you might be wondering, Raja, you said we never make negatively charged intermediates. Well, this intermediate is overall neutral, right? You end up with a negative charge on the oxygen and a positive charge on the nitrogen. We call this a zwitterion. So this zwitterion will then be protonated by whatever the most acidic thing in there, we'll talk about that in a minute, to give you this molecule here. And then this molecule will then be deprotonated by the conjugate base of whatever your acid is to remove the positive charge off the nitrogen to give you something that goes by several names, two names. So we call this a carbonyl amine, or it's also called a hemiaminal. Both of those names are appropriate. Now notice the similarity between the carbonyl amine slash hemiaminal and the hemiacetal, right? And here in the hemiacetal, you'd have alcohol attached to alkoxy group. We see the same pattern here, right? Alcohol attached to a nitrogen with a carbon on it, right? So the hemiaminal slash carbonyl amine is very similar in structure to the hemiketals and hemiacetals. So nucleophilic addition under acidic conditions. The second step here to get from here to the imine is very reminiscent of an SN1 reaction. Now in this case, instead of a full SN1 reaction, it's almost like an SN1 reaction with a rearrangement, right? So you protonate the oxygen here with whatever the acid is to make the oxygen a good leaving group. This oxygen leaves. Now, instead of something else coming in and attacking this thing right here, the nitrogen helps this oxygen leave, and then I can just deprotonate this this iminium intermediate. So this is actually called the iminium intermediate. I can deprotonate this iminium intermediate to make the imine. And so the difference between making the acetal and ketal and making the imine is that instead of something else and coming and attacking this intermediate, I can just remove a proton to get rid of that formal positive charge. Now notice that if I look here, I had the nitrogen attacking directly onto that carbonyl carbon. In these reactions, even though it's under acidic conditions, protonation of the carbonyl isn't the first step. The most basic thing in there is actually the nitrogen. So when I put a nitrogen with some kind of acid in there, the first thing that's going to happen is I'm going to protonate that nitrogen to make the ammonium salt. And this ammonium salt is actually the acid catalyst that's doing all the protonation. So up here in this previous slide, this HA, this A right here, is actually this thing here. That's what the A is here, right? The A is the ammonium salt, okay? And what you need is this thing is not acidic enough to protonate the carbonyl, but it is acidic enough to protonate the oxygen of this intermediate here, right? So all of these proton transfers that are happening, so here and here, these are all coming from the ammonium salt. And this brings up an important point. You can't be too acidic, because if you're too acidic, all your amines will be protonated and form the ammonium salts and not be nucleophilic. And if you're too basic, right, you're not going to have enough H plus in there to protonate those intermediates and make that mechanism happen. So it turns out that you need to be at a pH close to 5 in order for these types of imine formations to happen. Now, let's look at the same reaction. Instead of reacting with a primary amine, you react with a secondary amine. Now, when I react with the secondary amine, I get a much different product. I get something called an ene amine. The way this name is coming from is ene for the double bond and amine for the nitrogen here. So what's going on here? Why am I getting the ene amine here versus the imine? Simply by adding another carbon onto that nitrogen. So what we'll see is the mechanism is very similar to the imine formation, except for the very last step. So I have an amine here. That amine is nucleophilic enough to attack my carbonyl. I make this Zwitter ion intermediate. So remember, the Zwitter ion is when you have a neutral molecule with two formal charges, so a plus formal charge somewhere and a negative formal charge somewhere. So you make this Zwitter ion. That Zwitter ion gets protonated by the acid, so the O minus attacks the H plus. You make this ammonium intermediate, which is then deprotonated by the conjugate base of your acid to make your carbonylamine or hemiaminal. You then do the SN1-like reaction where you protonate the oxygen to make it into, you protonate the oxygen with the acid to make it a good leaving group. This oxygen then leaves, facilitated by the lone pair on the nitrogen. Now here, we've made the iminium intermediate again, but there's no hydrogen here. There's no hydrogen here or here to eliminate. So what actually happens is the conjugate base will eliminate a hydrogen on a carbon adjacent to this iminium intermediate. So you eliminate, so this is almost looking like an E2 elimination. So this is such a weird reaction. This is like a combination of the SN1 mechanism, right, where this leaves, followed by an E2 elimination reaction. So the conjugate base will remove the proton here, kick the electrons over and up to make the enamine. So again, if I take the same ketone and I react with the primary amine under acidic conditions, I make something called the imine. If I take the same ketone and I react with a secondary amine under acidic conditions, I make the enamine. Okay. Another reaction, another type of amine you can use are these these amines that look like where you have two nitrogens bound to each other. Super common. This is what we call hydrazine, and there's a number of different hydrazine-like molecules. And hydrazine actually turns out to be really, really nucleophilic. The moment you put two nitrogens next to each other, right, these electrons are being repelled by the other nitrogen, right? So these electrons are like, I want to leave, I want to leave, I want to leave. So what you can do with hydrazine is you can take a ketone or an aldehyde and very easily make this imine intermediate here. Once you have this imine intermediate here, you can use a strong base and heat and eliminate nitrogen gas to make the alkane. So this overall two-step process is called the Wolff-Kishner reduction. It's where you can take a ketone and convert it to an alkane. All right. And the first step is imine formation, which is like the primary. So we're not going to go over that mechanism. We're going to go over the mechanism of this second step here. So once you've made this imine intermediate, what happens under the basic conditions with heat, right? You're basically doing multiple elimination reactions to eliminate N2. So what's going to happen here is you have your hydroxide. That's going to remove one of the protons on this nitrogen here to make this negatively charged nitrogen. There's a resonance structure here where you can start making this molecule, the two nitrogens, start to look like N2. So I'm going to push these electrons down and put the electrons onto the carbon here. So this is now starting to look like N2. I can protonate that carbon using the molecule of water that you formed over here. And now you've added the one hydrogen to that carbon. I can do another elimination reaction. So in this case, what I'm going to do is I'm going to remove this proton, push the electrons up onto that nitrogen. And again, you get this same thing here, but instead of now pushing the electrons here, what happens is when these electrons kick down, they actually kick this out, and you make this carbanion here. And the reason, so look, making this carbanion isn't really great, but the reason why you can make the carbanion in this case is because you lose nitrogen gas. And again, Le Chatelier's principle rears its head and to allow you to do this. If I'm losing this gas, and what Le Chatelier's principle says, if I lose this nitrogen gas, the reaction is going to push itself this way. This is super, super basic. That's going to remove the proton from a molecule of water to regenerate your hydroxide and give you the reduced carbonyl compound. So one of the things I want you to keep in mind is that when you look at when you think about nitrogen nucleophiles, right? I want you to think about the similarities between the acid catalyzed additions with oxygen and the acid catalyzed additions with nitrogen. And one thing to keep in mind is that when you're under acidic conditions, right, the reaction species should either be neutral or have a +1 charge. And the major difference between nitrogen and oxygen nucleophiles is this ability of nitrogen to kind of attack twice. The oxygen nucleophiles, they attack once. So if I'm going to add oxygen twice, it's two different molecules of the oxygen, right? Whereas if I'm going to add nitrogen twice, nitrogen can add twice as long as it's a primary or a secondary amine. All right, that's it for nitrogen nucleophiles. Let me know if you have any questions, and thanks for watching.